Bond line structures, that'll be the topic of this lesson. And we've just covered condensed structures. And after this, we'll move on to talking about functional groups and resonance. But the topic of this one's going to be bond line structures, also called line angle structures as well. And so we're in the second chapter of molecular representations and resonance in my brand new organic chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I put one of these up. All right, so a bond line structure, obviously they call it a bond line structure because every bond is going to be represented by a line. Okay, not so bad. But these are kind of the epitome of organic chemistry laziness, or really, truth be told, organic chemistry efficiency. So because we draw carbons and hydrogens so ubiquitously, so in organic molecules, so again, it's all based on carbon, but the truth is we often have more hydrogens than carbon atoms. Well, the solution to being the most efficient as we can be in drawing structures is to just not draw in all the carbons and hydrogens. And you're just supposed to know where they are based on some rules here. So the first part is we typically don't draw in any carbon atoms in a bond line structure. So the way it works in a bond line structure is every vertex in your structure is a carbon atom. And so in this case, from this structure right here, we can see that we have 1, 2, 3, 4, and a fifth carbon right up here. This one's got 1, 2, 3 carbons. This one's got 1, 2, 3 carbons. This one's got 1, 2 carbon. So any vertex that's not labeled by default is a carbon atom. Now the second rule talks about hydrogen atoms. We don't typically draw all the hydrogens either. And specifically, don't draw the hydrogens that are bonded to carbon. We'll see one exception for an aldehyde functional group, but outside of that, we don't draw hydrogens that are attached to carbon atoms, that are bonded to carbon atoms. Cool. Now, not all hydrogens are bonded to carbon atoms, so we'll see that hydrogens that are bonded to anything other than carbon, we specifically do draw those. So, however, we don't draw lone pairs on all those atoms. And oftentimes we'll call those heteroatoms, meaning different atoms other than carbon and hydrogen. Carbon and hydrogen are found in almost all organic molecules, but whether you find nitrogen or oxygen or halogens, those just vary from organic molecule to organic molecule. So sometimes outside of carbon and hydrogen, we just label everything else as heteroatoms. But in this case, we do draw hydrogens that are attached to these heteroatoms, but we often typically don't show the lone pairs. Now, I say that a typical bond line structure or line angle structure doesn't have to put lone pairs on those heteroatoms. However, you should be careful. Typically, your instructions on any exam you're likely to see this year, especially in the first semester, are going to say you should draw all lone pairs on every structure you draw, including bond line structures. So it's technically not required for a bond line structure, but we usually require it of all of our undergraduates to make sure they know where all these lone pairs go and stuff. So let's kind of see how this works. So in this first structure, we're going to turn this into a Lewis structure, and this vertex right here represents a carbon, and that carbon has no formal charge. So if it had a formal charge, we'd have to list it like on these two. So it's got no formal charge, and when carbon doesn't have a formal charge, he's going to typically have 4 bonds, almost always, in fact. So in any example you're likely to see anytime soon. So in this case, this carbon right here is bonded to, and let's just set up the skeleton of carbons here. A carbon right there, that carbon right there is bonded to a carbon up here. That carbon up here is bonded to a carbon over here, and that carbon over here is bonded to a carbon over there. And that's kind of the carbon skeleton here. And none of these carbons have a formal charge. So we know they all have filled octets then. And that means they're going to have 4 bonds for a neutral carbon. And so we're just going to add hydrogens because those aren't drawn in either until it's got 4 bonds. So like this carbon right here only has 1 bond showing, and that means he must have 3 bonds, 2 hydrogens. Same thing with this carbon up here. He's only got 1 bond showing, so he must have 3 bonds to hydrogens. Now this carbon right here, he's got 1, 2, 3 bonds showing. So to get a filled octet, he's only going to need 1 bond to hydrogen. This carbon right here has got 2 bonds showing, so he's going to need 2 bonds to hydrogens. And then finally, this last carbon has only 1 bond showing, so he's going to need 3 more bonds to get to 4 and a filled octet. And there indeed is our corresponding Lewis structure. Now, cool, notice I've showed angles here a little bit to more accurately reflect the geometry here. Now, a Lewis structure, Lewis usually made everything look like 90 or 180, so this might not quite look like a typical Lewis structure you're used to seeing. But I tried to represent it in the molecular geometry here. Now, these bond line structures are also called line angle structures because we also, in addition to representing every bond with a line, we try to represent the angles, the bond angles, accurately as possible. And that's why I've kind of tried to represent this Lewis structure as much like the bond line structure as possible as well. We'll do the same thing here. So in this one, we've got 3 different vertexes that are not labeled. So that's going to represent that we've got 3 carbons. So, and in this case, once we set up our carbon skeleton, we're going to worry about that last one because he's got a positive formal charge. We'll have to figure out what in the world that means. But the ones on the ends here, they're neutral, and being neutral, we should expect those carbons to have 4 bonds. So any bonds they're missing so far after we've set up our skeleton should be hydrogens. So this carbon right here only has 1 bond showing. To get to a total of 4 bonds, we're going to need to draw 3 hydrogens in. Same thing with the other one on the other side. He's only got 1 bond showing, so we're going to need to draw in 3 more bonds. But that one in the middle, you might look at this and be like, Chad, he needs 2 more bonds. And don't draw this in yourself just yet, because I'm about to erase one of these. But we might be tempted to do something like this. But if this was the case, this carbon would have 4 bonds, which is normal, and he would not have a formal charge. So we would take 4, the normal number of valence electrons for carbon, and subtract 1, 2, 3, 4. So 4 lines, no dots. So 4 minus 4 is 0, no formal charge. But we're supposed to have a positive formal charge. What that means then is we're going to have to erase one of those hydrogens, and now we do 4 minus 1, 2, 3, and that would be a positive formal charge. So this is an example of a carbon with no filled octet. So he's not making his normal number of 4 bonds, he's only making 3. So, and oftentimes to reflect the geometry a little better, so this guy's actually going to be sp2 hybridized, which means he's trigonal planar. Bond angles are 120. And so oftentimes we draw that 3rd hydrogen here to reflect that trigonal planar geometry. So we'd also represent that formal charge on the carbon like so, similar to the way it looks in the bond line structure. Cool. So we call this a carbocation, by the way. We'll revisit these a little bit down the road. But a carbocation is just a carbon with a positive formal charge. And generally, you're going to see those pretty frequently in this course. And they're going to have 3 bonds and no lone pairs to end up with that positive formal charge. Now, this next one here is a carbon with a negative formal charge. And once again, we'll set up the carbon skeleton. So 3 unlabeled vertexes. Those are all carbons. Once again, the ones on the ends have no formal charge, so to get them to 4 bonds, for both of them we'll add 3 hydrogens. And again, if we did the same thing with this guy, and gave him 2 hydrogens that he'd have 4 bonds, well then he'd have no formal charge. But we gotta have a negative formal charge. And so in this case, the question is, how do we get to a negative formal charge? Well, in this case, we can't go over the octet rule or anything, but we are gonna erase one of those hydrogens, and in its place, put a lone pair of electrons. And if you again notice, carbon's normal valence is 4, and we'll subtract the dots and lines, and he's got 2 dots, 3 lines, and 4 minus 1, 2, 3, 4, 5 is negative 1. 4 minus 5 is negative 1. And that's how we get a negative formal charge. So we call this again a carbanion. So we had carbocation over here, carbanion over here, which is just a carbon with a negative formal charge. And to accomplish that, you should file it away in your head because we'll see these on a regular basis throughout the course of the year as well. So you're going to have a carbon with 3 bonds and a lone pair of electrons. Oh, and I forgot to draw a couple of hydrogens. Let's just get those in because that just looks horrible otherwise. Cool, we've got one last bond line structure to do here. And so this is a functional group we'll learn about in the next lesson called an amide. And in this case, we've only got 2 vertexes that are not labeled. So we've got and let's do this down low here. So carbon, carbon, nitrogen, oxygen, and we can see that even that's a double bond. Okay. So we'll start off with those carbon atoms, and again, we need to add hydrogens to those carbons, and this carbon right here, so it has no formal charge in the structure, so he's going to have 4 bonds. And in this case, to have 4 bonds, we need to add 3 more hydrogens. But this carbon right here already has 1, 2, 3, 4 bonds. He's good. He doesn't have any hydrogens whatsoever. Cool, notice we did have to draw a couple hydrogens in here, and that's the thing I wanted to point out with this example is put a couple heteroatoms in there, and I wanted to point out that if they're bonded to hydrogens, those actually have to be included in the bond line structure. It's only the hydrogens on carbons that are not going to be included. All right, now what's not included though are lone pairs of electrons. Now if oxygen and nitrogen don't have formal charges, then we got to be like, okay, well nitrogen usually gets 3 bonds, he's got 3. Oxygen usually gets 2 bonds, he's got 2. But if we don't show their non-bonding pairs of electrons, then how do I know they got a filled octet and stuff? So in this case, we're going to add those lone pairs in. And in our case with oxygen, we're going to have to add 4 electrons because he only had 4 around him. Now he's got a filled octet and he's got 8 around him. Nitrogen here's got 2, 4, 6 around him. He's going to need a pair on him as well, and now he's got a filled octet. And so for hetero atoms, we generally add lone pairs until they got a filled octet when you're going from the bond line structure to the Lewis structure. Cool. So you got to typically draw hydrogens in on carbons, and you got to typically draw lone pairs in on all the rest of the atoms. All right, so now we've learned how to turn bond line structures into Lewis structures. Well, in the last lesson, we learned how to turn condensed formulas into Lewis structures as well. And the truth is we got to be able to interconvert between all 3. We've got Lewis structures we learned in chapter 1 and something you learned back in Gen Chem. And now we've also learned how to draw condensed formulas and bond line structures and how to convert them back and forth with Lewis structures. But now you've got to convert them back and forth with each other. So you've got to be able to turn condensed formula into bond line structures and bond line structures back into condensed formula. And usually I recommend students start off by using the Lewis structure as the intermediate or the intermediary between the two. So what I mean by that is this. So here we've got a condensed formula. So back in the last lesson, we learned how to convert this condensed formula into this Lewis structure. Now we want to convert this Lewis structure into the corresponding line angle formula. And the way you do this, you just kind of look at your longest chain all the way through. In this case, it's 1, 2, 3, 4, 5 carbons. And you're just going to start zigging and zagging. It doesn't really matter if you zig up or down first. So, and the key is don't count the number of lines you're drawing, count the number of vertexes. 1, 2, 3, 4, 5. Notice 5 vertexes only needed 1, 2, 3, 4 bonds. That's what I mean. Don't count the number of bonds, count the number of vertexes. So 1, 2, 3, 4, 5 to match up with 1, 2, 3, 4, 5. In this case, we don't draw any of the actual carbons. They're there by default as the vertexes that are not labeled. And then we don't have to draw any of these hydrogens in because those hydrogens are all bonded to carbon. This actually is the entire bond line structure. Second example I want to look at is also one from the last lesson. In fact, the next several we're going to do are all from the last lesson. We converted such condensed formulas into these Lewis structures, and that's why I'm just kind of taking this by default. You probably already have this in your notes from the last lesson. So the question is now, how do we turn this into a bond line structure? Well, once again, you want to find your longest carbon chain going right across. So 1, 2, 3, 4, 5. I just drew a long bond so we could line things up here. So, but 1, 2, 3, 4, 5. And so we'll just do some zigging and zagging again. So 1, 2, 3, 4, 5. And I'm counting my vertexes 1, 2, 3, 4, 5. And on the second one in, I need a bromine. Now, one thing you should realize, we've got 2 different areas coming off this carbon. We've got this little area down here, and we've got this big area up there. When you start drawing in additional bonds on a bond line structure, don't draw any more into this little area. Always put them into this big area here. So I like to think these 2 atoms right here, or these 2 bonds, I should say, form an arrow pointing up, and it's up where you put the additional bonds. Whereas these 2 right here, once again, you've got this little area right here, you've got this big area right here, and again, if we have to draw additional bonds coming off that carbon, we're going to draw them in this big area here. So again, these 2 bonds right here form an arrow pointing down, and that's where we're going to draw the next bonds if we had to draw any additional bonds here. So let's look. For this second carbon in, we do have to draw an additional bond to a bromine, and so we'll draw that up here, not down below. We'll get those out of there as best I can. And on the next carbon over, we've got a CH3 to draw in. And so in this case, that's going to go down here. Now, we don't actually have to draw anything except an unlabeled vertex, because that unlabeled vertex is a carbon, and it's bonded to as many hydrogens as it needs, in this case 3, to get that filled octet. So that's all we draw in right there. I'll erase this as best I can without looking too terrible. Cool, and then we move on, and that was the 3rd carbon in the chain. The 4th carbon in the chain is there, and the 5th one is right there, and that is the entire bond line structure. All right, these next 2 structures are also from the last lesson on condensed formulas. So we already turned these condensed formulas back into Lewis structures back in the last lesson. So I'm kind of taking that we've already done that so far. So, but if I asked you to turn this condensed formula into a bond line structure, the first thing you'd probably want to do at this stage of the game is turn it into a Lewis structure. And then once you've got that Lewis structure, you can turn that into a bond line. Now, eventually you'll get pretty good at this, and whether you draw it in the condensed formula or the bond line, you'll pretty much be pretty good in all likelihood at converting those back and forth without having to go through the Lewis structure. But for now, I would highly recommend going through the Lewis structure to get back and forth between the condensed structure and the bond-line structure. All right, so if we want to turn this Lewis structure that came from this condensed formula into a bond-line structure, you look for your longest carbon chain, 1, 2, 3, 4, 5. And we'll zig and zag here 5 times. 1, 2, 3, 4, 5. I should say we'll zig and zag 4 lines, but 5 vertexes. So, and now that we got our 5 vertexes, we'll go back in and we realize that between our third and our fourth, we've got to put a double bond right there. Cool. So this would be one way to demonstrate this. So it turns out this is not the most specific, although we could say it is. And maybe I actually haven't drawn the right one, but it turns out that double bonds cannot rotate. When you've got sideways overlap of p orbitals, if you try to rotate that bond, so it's just not possible. You'd have to break the pi bond. So you'll learn a little more about this in the next couple of chapters. So, but it turns out there's one other possible way to represent this with that double bond. And instead, so we'll still put that double bond in there, but instead of having this zag down, or zig down, we can have it zag up or something along those lines. And it turns out we'll find out that these are examples of what we call cis and trans isomers. So, and that's not important for now. Super not a big deal if you didn't see one of these coming. I'm just trying to cover all my bases. At this stage of the game, whether or not you drew this one or this one, both are pretty acceptable. And in fact, drawing both will be the most complete and most correct answer, but it's not usually something we're expecting of you at this point until we teach you about cis-trans isomerism a couple chapters down the way. So if you didn't come up with one of these, no problem. It's not going to be required of you at this stage. I just wanted to cover my bases in case some of you drew this one and some of you drew this one and you didn't know what's going on. So they're both acceptable. All right, this next one here, same kind of thing. We've got our longest carbon chain. So again, this is also again from that last lesson. So we've already got the Lewis structure, and then we'll take and convert the Lewis into our bond line structure. So 1, 2, 3, 4, 5. So, and we'll draw a 5 carbon chain. And again, I start by zigging up, but you could have just as well started by zigging down instead. Doesn't matter. Totally arbitrary. So not one right way to draw this in that respect. So, but I'm going to do it like so. And again, all the rest, we got 5 vertexes, which stands for 5 carbons. And the rest of this is all hydrogens. And so we might just think, well, just get that triple bond in there and we're done. But we have one major problem. So again, these bond line structures, we try to actually get the bond angles correct. So again, sometimes they're called line angle structures. And so if you look back here, like this angle right here, well, this is an sp3 hybridized carbon. And so the bond angles around it are all 109.5. And if you look at that, I'm not going to pull out my protractor or anything, but that kind of looks like 109.5. Cool. Now, these 2 carbons right here are just sp2 hybridized. And so the bond angles are 120. Well, notice the difference between 109.5 and 120, it's not a big difference. And if you look at this, I'm like, I could pull out the protractor and maybe I'm off by a little bit one way or another, but whether it's 109.5 or 120, whatever, it's close. Cool, but we don't have that here. So here, this is a triple bond. These 2 carbons right here are sp hybridized. And sp hybridized carbons are have 180 degree bond angles. And I can look at that, and I don't know if that's 109.5 or 120, but I know it ain't 180. And so when you've got a triple bond in your chain, you want to make sure you get your bond angles correct. And so what we often have you do is start with the triple bond. So this is technically wrong. Don't want you to draw this exactly like so, but start with that triple bond. So, and these are both carbons right here, and you've got one more carbon coming off to the right. And then you've got 2 more coming off the left, and you want to make sure the first one comes off at a 180 degree bond angle. And whether this one zigs up or zigs down is totally up to you. But again, this represents 1, 2, 3, 4, 5 carbons. A lot of students have a little trouble with this one, not recognizing that that vertex right there is a carbon, and that vertex right there is also a carbon, and we have 1, 2, 3, 4, 5 carbons in the chain. But with a triple bond, make sure the 2 bonds coming off, the sp hybridized carbons are coming off at 180 degree bond angles. All right, these last 2 examples, once again, also from the last lesson on condensed formulas. In the last lesson, we turned each of these condensed formulas into these 2 Lewis structures. And again, the goal here is to turn these 2 condensed formulas into the corresponding bond line structures, which again, I highly recommend you do by drawing the Lewis structures first. But we already did this in the last lesson, so I'm not going to repeat that. But now we're going to take these condensed formulas, which we turned into Lewis structures, and now turn them into bond line structures. And again, find your longest continuous chain. So in this case, 1, 2, 3, 4, 5 carbons. And so once again, we'll zig and zag till we've got 5 vertexes. So 1, 2, 3, 4, 5. And then we'll go back, and between carbons 1 and 2, we're good, but between 2 and 3, so that's carbon 2, carbon 3 here, from the end, we'll put a double bond. And then coming off carbon 4 from the left, we'll put a double bond to oxygen. And from there, everything else are hydrogens that are bonded to these carbons that aren't going to get drawn in. And this is your bond line structure. And once again, so we've got a double bond, and once again, you could have drawn that potentially one other way. Just cover my bases. Whether you draw it one or the other, you're probably okay at this stage of the game. Oh, I don't need lone pairs technically either. So, and you could have drawn it like this as well. But again, this is based on you guys understanding cis and trans isomerism, which again, we'll get to later. So I don't really care if you came up with one of these or the other. So it wouldn't necessarily be required of you to come up with both at this stage, but that's coming a couple chapters down the road. One thing to note, if you were converting this lovely condensed formula into these, on your likely organic chemistry first semester exams, they're going to say, oh, by the way, make sure to draw all lone pairs. And so even though a proper bond line structure doesn't actually need lone pairs, on your exams, you're probably going to need to include them. And so you're going to want to get in the habit, even though your professor is likely to not draw them in because they're not required for bond line structure, you're going to want to get in the habit of including them always because it's in all likelihood going to be required of you on your exams. All right, last example here. So this was that carboxylic acid. And again, we've got this condensed formula. We've already converted it into a Lewis structure in the last lesson. And now we want to convert it into the bond line structure. And we've got 1, 2, 3, 4. And we could even call this a fifth, even though it's not a carbon. We'll label it appropriately. So zigzag till we've got 5 atoms in the longest chain. But the last atom on the right is not a carbon, it's an oxygen. So we've got to label it. So before I put that oxygen and drew that in, that looked a whole lot like a carbon, an unlabeled vertex. But once I label it as an oxygen, now I know it's not a carbon. So we've got 1, 2, 3, 4 carbons and then an oxygen. So 1, 2, 3, 4 carbons and an oxygen. This carbon's also double bonded to another oxygen atom. This oxygen's also bonded to a hydrogen. But the rest of these hydrogens are all bonded to carbons and they're not going to show up in the bond line structure. And once again, this is the correct bond line structure, but once again, you should include your lone pairs and get in the habit of doing so, putting those lone pairs on the heteroatoms. Cool, but there's your bond line structure with lone pairs of electrons drawn in. All right, last thing we want to do in this lesson is we want to now take some bond line structures and turn these back into Lewis structures. And technically, they could even ask you to turn them back into condensed formula. But I just want to go back to Lewis structures. I'm confident that you guys now know how to convert between condensed formula and Lewis structures back and forth. But I would definitely want to take an example, or 3 examples here of converting bond line structures back into Lewis structures. So if we look at this first one, we've got 4 vertexes that are not labeled. So that's going to be a 4-carbon chain. So, and in this case, the only one that's got a formal charge is this carbon right here. So we'll worry about him last, but the rest of these, we just need to add enough hydrogens in to get them filled octets. So this carbon here only has 1 bond showing, so we have to draw in 3 hydrogens. This carbon right here has only got 2 bonds showing, so we've got to draw in 2 hydrogens. And the carbon on the right has only got 1 bond showing, so we've got to draw in 3 hydrogens. Now this carbon right here has a positive formal charge, and I'm going to rely on the fact that earlier in the lesson we learned that for carbon to end up with that positive formal charge, he's going to only have 3 bonds, not 4, and no lone pairs. And so in this case, instead of giving him 2 hydrogens, I'm only going to give him 1, and whether I put it on top or bottom is totally irrelevant. So, but normal valence electrons for carbon is 4 minus dots and lines. Well, he's got 3 lines and no dots, and so 4 minus 1, 2, 3 is indeed +1. That's how we end up with that positive formal charge. Cool, we'll move on to the next one. We've still got this same 4-carbon chain. So, and in fact, the 3 carbons that don't have a formal charge are identical in both these structures, so I'll just repeat what we did there. But now we've got this one here with a negative formal charge. And again, earlier in the lesson, we pointed out for carbon to end up with a negative formal charge, he needs to only have 3 bonds, not 4. But in addition to those 3 bonds, have a lone pair of electrons. That way, when you go calculate formal charge, again, carbon's normal valence is 4, 4 minus the dots and lines. In this case, he's got 2 dots and 3 lines. So 4 minus 1, 2, 3, 4, 5 is indeed -1. That's how we get carbon negative formal charge. And there's our corresponding Lewis structure. Now this last example, this is the first example where we've seen a dot, and a lot of students don't recognize that as anything more than a dot, but that is like this, except there's only one electron there, non-bonding electron. And when you've got one non-bonding electron, we obviously don't call it a lone pair. We just call it a radical, it turns out. When you hear the term like free radicals or, giving me cancer and things of this sort, free radicals just mean you have an unpaired electron somewhere. Now, back in chapter 1, I actually lied to you. I was totally wrong. I said you're never going to encounter a situation where you have a violation of the octet rule where you have an odd number of electrons. Actually, I was wrong. No, we're going to see radicals every once in a while in this course, but we're not going to usually look at them in the context of the octet rule. So technically I was wrong in chapter 1, but you're not going to see an example where we have to analyze this in the context of the octet rule. So if we look at this, though, we have the same kind of thing. We've got these 3 carbons match up with same 3 carbons on these other structures. So first one here. So it's got 3 hydrogens. The next one, only having 2 bonds showing, is going to have 2 hydrogens. And then again, the one on the end, so with no formal charge, 1 bond showing, and he should have 3 hydrogens as well. Now this one right here is the one with the unpaired electron. They had to show that unpaired electron. But in this case, there's no formal charge. He's not positive like this one. He's not negative like this one. He's still got a 0 formal charge. He's neutral, but he's a radical. He's got an unpaired electron. But in this case, I can't give him 2 hydrogens. Notice there's not room. I'd have to go over the octet rule. But in this case, he gets 3 bonds and just has that unpaired electron. There's no charge. And again, if we do the normal formal charge rule, so 4 is the normal valence for carbon. And in this case, he's got 1 dot, 3 lines. So 4 minus 1, 2, 3, 4 is indeed 0. And so we'll find out this is another example of a neutral carbon. But you can distinguish it from a neutral carbon like this because we have to show that unpaired electron as part of the structure, whether it's on the bond line or whether it's on the Lewis. It's going to show up in both. Otherwise, we can't distinguish the two. Now, if you found this lesson helpful, consider giving me a like and a share. And if you've got questions, feel free to leave them in the comments section below. Now, if you're looking for the study guides that go with this lesson, or if you're looking for practice materials, check out my premium course on chadsprep.com.